So thank you so much, Ryan, and everybody for inviting me to come along. And I'm looking forward to giving this talk to this group because I think it's not often that you get to see the evolution of a product from a research idea to something that goes out into the world and hopefully will help people in their real lives. And so this is the story of the Codex. Here's a picture of the Codex. And eventually I have one here beside me. I can show it to you afterwards. So the Codex is a 4-line 32-cell Braille display, and we'll find out about its features and how we got from the concept to Codex in the course of this talk. So the motivation for developing a multi-line Braille display was to provide a reading experience for blind people, a digital reading experience that was as rich as the regular reading experience for reading books. This might sound kind of strange, but most Braille displays that are out there at the moment are single line Braille displays. And as we'll see, that's not necessarily how we read Braille. We like to have more lines for reasons that will become apparent. And we'd like to go beyond this reading experience to do much more to include, for instance, dynamic content, interaction with the Braille text directly, and so on. So this slide here kind of is designed to show you what the state of the art looks like right now. So you'll see the first 2 lines are 20 characters, the next 2 are 40, and the bottom 2 are 80. So most of us typically have a 20 character display, so that's all you can get on one line, basically. Some of us have 40 character displays, and very few people have 80 character displays. They currently cost about close to $7,000. And so you can just see roughly how much text you can get on a line. And given that you only have a single line, that's kind of the window into the text that you have at any one time. So one question that we're often asked is why bother with Braille? If speech is ubiquitous and free, it comes for free on many phones and even on PCs, you can download free screen reading software. Why bother with Braille? Well, it turns out Verasusa et al. Have looked at the difference between reading and listening, and they found out that in many cases they're not equivalent. When they had people, so they tested people reading text or listening to text or reading text themselves, reading text out loud or listening to text, and they found out that people's minds wandered more when they were listening to things than when they were reading text themselves. And the listening group, the group who only listened, also scored much worse on memory in terms of remembering what the passage was about afterwards. And listening even led to people reporting less interest in what they were reading than when they were reading the text themselves. So even for reading, it turns out that it's a good idea to have physical orthography, like a text that's equivalent to print, rather than just having people listening to books. And of course, most of the time we do end up listening to books because that's where they're more available. And the thing about Braille too is that there are many Braille codes which don't fit on a single line, such as math and music and other scientific notations. And it would be really nice to be able to have refreshable versions of those codes available as well, preserving their typographical content, context, and relationships. So here's this is me exploring a diagram of the tube map in London, and you can see that, you know, it's obviously helpful here to have some spatial extent and not just a single line. So my dream in working with, in starting this whole project on developing a multi-line Braille display was to come up with a richer reading experience for blind people, but even to go beyond that, to develop something that was interactive and could support many more kinds of notational. But if we want to achieve this, there are a number of things, challenges we need to overcome, and that's what we're trying to address in some of the studies that supported the development of the Braille display. So this is the Holy Braille. I didn't come up with this title. So the search for the Holy Braille, which is the multi-line, fully interactive tactile display. This has been the dream of not just me, but many blind people right back when even single line Braille displays first came out. So if you have multi-line displays like this, you can interleave Braille and tactile graphics so you can actually label your images, your tactile images. And obviously you can support Braille codes like music and math that require spatial extent. And you can even develop new typographies for Braille that, for instance, might use different dot heights and so on. And then text display and the manipulation of text can be co-located on the same surface. And so, yes, in this world, we can encompass interactivity. This is me reading Braille on a single line 20 cell device. This has a button above each Braille cell, so you can route the cursor to the current cell. And this is pretty much the state of the art. But here's the Codex. This is our display. And you can see here now that the whole surface is now interactive. So when I find a menu item here, I can just double tap on it to activate it. And I can read the whole menu at once, at least 4 lines of it anyway. So you can already see that this is a great step forward. And in fact, this is how we route the cursor on our display. You basically just tap on wherever you are and the cursor comes to you. And then you can just edit where you are. So when you're developing something like this, a key design consideration is that technological solutions are necessary, but they're not sufficient. We could come up with a fantastic way of actuating dots, and we'll see some of the challenges in doing that later on. But unless we actually think about why and how people read and what they want to do with a device like this, it's not worth it. We're wasting our time and our money. So, in thinking about designing for any kind of interactive system, this is the thing that I always tell students. It doesn't matter what you're doing, you really need to approach your problem this way. First, design the task or figure out what the task is. Then determine the perceptual motor capabilities of the body that you're drawing on. So are you looking at large scale or fine grained movement? Do you need people to see what you're doing? Do you need them to use their hands or their feet? If we're thinking about digital musical instruments, what kind of expressive modes do you want to support? So first figure these things out. And the last thing you do is figure out the technology. And the neat thing is if you do it this way, and you end up with an interaction design that's really robust, so that if a different technology comes along that will do a better job, you can switch it out underneath and you can keep your interaction design and it shouldn't impact what you're doing. So with that in mind, this is the approach that we took to designing the Braille display. So first then thinking about defining the task. So in order to do that, we have to think about how blind people read Braille, how this can inform the design of the Braille display, and how we can move beyond just static reading to more interactive systems that allow you to do more with Braille text or even tactile graphics. So let's answer this first question first. So how do blind people read Braille? And it turns out that the nature of people's hand movements when they're reading Braille is very complex. And the way people move their hands is determined by what they're trying to find out, basically. So observing how somebody is moving is going to tell you quite a lot about what they're trying to do. This is true of all haptic interaction, in fact, actually. So here's a really cool video. This is me reading Braille, but it's based on work by somebody called Eatman that was done actually in the 40s, where she had a light box and she had people read Braille on a transparent surface to look at how they naturally read, just given no prompts. And here you'll see what's happening is that I'm using what's called a butterfly technique, whereas when my hand is getting to the end of one line, my other hand is already going back to start reading the next line. It's not that you read both the end of the previous line and the beginning of the next one at once, but it's just that you use the left hand to start to go back so you find the right starting position for reading the next line. And this turns out to be a really efficient technique for reading existing hard copy Braille. Okay, so that's an interesting thing. And then here's the same image, but now I'm reading music, and this is piano music. So you can see that what I'm doing is we've got a left hand and a right hand of the piano part, and I'm going between the two, going up and down to look at alignment between the notes in the left hand and the notes in the right hand, and trying to figure out what the music is doing as I'm doing that. So you can see the hand movements here are very different. So that's something that's important to know if we're trying to design an interactive Braille surface. So then the question becomes, how can this inform the design of an interactive tactile Braille device? And so we can learn about all sorts of things from the literature already. Um, so here are some parameters that we know. These have to do with the actual physical Braille display, like what should be the distance between dots, how high should dots be, and you can see here there's a sort of minimum, maximum, and normative values for all of these things. These are pretty much standardized now. European Braille is a little bit smaller than US Braille, but not much because it has to fit under the fingertip. Um, and fingertips of different size people. So this is sort of where it's landed, basically. Um, yeah, so all of this is all stuff that's in the literature already, and obviously when we're designing the surface, we adhere to these parameters so that we would make Braille that people would enjoy reading. But some parameters we don't find in the literature, so we have to look for them ourselves. And so I have 2 years of studies that I want to highlight here, which kind of helped us answer some questions along the way. So this first example is a bit of a Mythbusters study. So if I had $1 for the number of times people had come up and said, "Oh, well, you only need one Braille cell because your finger's only on one Braille cell at a time," and it turns out that that's not actually how you read Braille. So what we wanted to discover was what is the role of lateral motion and basically skin changes in skin deformation and the role of proprioception, which is the sort of movement of your arm as you read Braille, because obviously these two things happen as you touch and read a Braille text. And the claim of this study was that both relative motion between the fingertip and the reading surface and the proprioceptive feedback you get as you move your arms and hands around the page are important aspects of active Braille reading. And we wanted to quantify the contribution of each of these to the process of reading Braille. So we made we made these devices, and so this we call these two versions of the apparatus mouse and clock. The mouse basically was the equivalent of putting a single Braille cell on the back of a computer mouse, and when you move the mouse, the Braille would refresh under your finger. So here the Braille is moving so you have proprioception because you're moving the mouse and the Braille is changing, but your finger is not moving against the surface, so you don't really have lateral motion. And the clock is even more constrained. It's just where you lay your finger across the surface of a couple of cells, and you might see time changing under your finger, but your finger isn't moving sideways. It's just the Braille is refreshing under your fingertips. So that they were the first two conditions. So in neither of these conditions, in both of these conditions, Braille is static, but one has proprioception, the other doesn't. And we compared those to these two conditions. These two, which we call line and tape. Line is just the normal case where the Braille is still and you move your fingers along the surface. The tape is like imagining something rolling under your fingers. So your fingers are still, and now the Braille is moving beneath your fingers. In both of these cases, there is lateral motion between the fingertip and the Braille. In one case, there's no proprioception again, in the other case, there is. So we could have predicted this, but what we did actually find, and I should say that what we did for this study was we had people read uh, letters out loud from random groups of letters, of 5 letters that we presented, and we looked at accuracy and speed as measures. But we also asked them about, at the end, to rank their conditions, the 4 conditions, to tell us which they preferred. So we found that as far as error rate and reaction time was concerned, the lack of sliding contact definitely impacted how accurately people read and also how quickly they responded. And the faster we presented the letters, the more errors we got. And so we concluded there that Braille displays that don't incorporate sliding contact, like the mouse and the clock condition, lead to more errors. So that was basic. There were some other findings from that paper too, but they were the ones that were that stood out most. And this second study is a bit more strange if you don't understand the role or the market of Braille displays. And in fact, we did this study predicting that this could happen, and in fact, it has. So it turns out that there are multi-line Braille displays out there, but the two that are not our device have this. They use this very strange electrostatics, sort of. I'm not exactly sure how the dots are raised, but it involves not being able to touch the dot directly and not being able to touch the dots while they're changing. So in order to avoid touching the dots directly, they've put this thin film over the Braille display, which means that you get a sort of low pass filter basically across the top of the Braille. And even though we didn't know that that's what was going to happen, we predicted that could happen. And so this was one of the motivations for this study. So we realized that if you wanted really good tactile graphics, you were going to have to go for a very high density dot display. But that was going to compromise Braille, which has a fixed inter-dot distance, if you like. So this is the motivation here, that these displays are typically composed of pins. So if you want to create a display that does really good graphics, you're going to have to have the pins very close together, but this is going to compromise the quality of the Braille that you can produce. So we wanted to figure out if you did have to pack pins close together, how could you get around this? And so we looked at a bunch of different configurations. These were physical prototypes mimicking what might happen if you packed lots of dots together and had to make Braille out of shapes combined of lots of dots with some kind of film stretched across them. So we looked at several configurations. So we wanted to know, how did different configurations of high density pins affect reading accuracy? And are multi-pin configurations in place of a single Braille pin viable? They work? And how could you compare them to solid shapes that you might make by covering these multi-pin Braille representations with this kind of film like we have on these devices now? And is it important for normal Braille dots to be separated, or can we make the shapes of Braille letters out of dots that are joined together? So what we had participants do, we made up these physical templates with these different kinds of shapes, and we had participants read sentences from a battery of sentences called the MN Read, the Minnesota Read corpus. And these are simple sentences that are controlled for the appearance of different letters and words and so on. And so we presented the sentences to participants in one of 8 configurations, 4 sentences being randomly assigned to each. And at the end, we asked people to rank the 8, the different reading formats, or the different dot formats from their favorite, or the easiest to read to the hardest to read. So here's the table that shows the stimuli. So some of them you can see are shapes like squares, X's, crosses, diamonds. And there are these 2 conditions. One is the standard Braille, and the other is what we call pokey Braille, which is the standard Braille spacing, but with very skinny dots. And so, yes, as this says, normal dot Braille was compared to this very thin Braille, and up to all of these other conditions. So the best condition obviously was normal Braille, but the next best condition was pointy dots, which we did not expect because they're quite hard to read. But it turns out that what people want preserved is interdot spacing and dot numerosity. So they want to be able to count the number of dots in the cell and know exactly where they are in relation to each other. And that makes sense because they're the 2 dimensions along which letters and numbers and everything are separated in the Braille code. Dot numerosity and dot placement are what are key to creating different Braille characters, and then to obviously being able to identify them. And it turns out the dots, where we made blobs that kind of conformed to the shapes of letters, these were the worst. These produced the worst performance in reading. Yeah, so that was it, and people hated. So they preferred obviously their favorite was Braille, then pointy dots, and then after that it was kind of noise. But the worst of all were the blobs. So we've talked now about the first part of our three-part thing, which is first understand your task. The next thing then is figure out the sensory motor capabilities that you're going to draw on for people when they're doing your task. And here we found in the literature we found a lot of information. So we know that many aspects of haptic and tactile perception can affect how people read tactile images in Braille. So obviously there's a limit to the spatial and temporal resolving power of the tactile system. So on the fingertip, we're typically looking at a, a 2-point threshold, or there are other ways of measuring it too, but an acuity of about 1 millimeter. And temporal integration is about 200 hertz. And then there's also some issues arising from systematic distortion, because if you move your arm in what you think is a straight line without looking at it, you'll actually make a curve that kind of basically follows the way your joints want to move. So there's a bit of a parallax error that creeps in there if you're not careful. So yeah, this is what I was saying. The spatial resolution of the fingertip is 1 millimeter, and the temporal response of the skin to successive stimuli is 200 hertz. And here are the information about Braille dot spacing again. Is about 1.5 millimeters, so it's a little bit above the threshold, but with Braille, you're trying to squish as much Braille onto the page as you can because it takes up a lot of space. So you're trying to find that nice space where you can get the whole letter under your finger, but you are not, the dots are not so close together that they're going to be blurred perceptually. Then the next issue is reading speed. So it turns out that Braille reading is slower than visual reading. Experienced Braille readers on average read around 150 words per minute. Now, there's some super readers that can get above that, but for most normal, very efficient Braille readers, that's about the normal reading speed, and that's about half the speed of reading print, because it's harder to jump ahead and it's harder to kind of keep track of lines and so on. But so we have a shorthand basically that compresses Braille to try and help improve that. So here's the word Houston. It's 7 letters, but when we abbreviate it using standard grade 2 Braille, it gets down to 5. That might not be much of a reduction, but there are some words that can be even more compressed using Braille abbreviations. So I'm skipping over a lot of things here because I want to move on to part 3, which is the bit that probably you're most interested in, which is getting finally, once we've got all those things in place, to figure out the design of the technology. So we made some key design decisions here, and we decided not to compete with the people doing tactile graphics. We're going to basically focus initially on doing really high quality Braille in multi-line format. We also want to support multi-finger tactile input so that you can actually move your fingers on the display and have something that seems like a much more natural interaction. Blind people are already used to doing this because we use iPhones and things like that. So we're used to multi-touch and negotiating icons and things on screen. So to sort of the current full page tactile displays out there at the moment only allow you to have one finger on the display at a time, as I mentioned, and you can't have your hand on the display as it's changing. And we kind of felt that that's a very unnatural interaction, so we wanted to avoid that. And then we wanted to develop some new techniques for interacting with Braille content and also with more dynamic tactile information. So let's talk first about focusing on Braille. So here's our first prototype. This was probably 2014. And you can see here that we have dots, but each of them has a separate pipe. So the decision we made was to use air. So we're using air to drive bubbles that raise and lower dots. And the reason for doing that is it's really hard to get an actuator that's strong enough to move a dot underneath the dot itself. And that's kind of the challenge with making a high density Braille display. You've got to find a way to drive the dot with an actuator that doesn't take up much more space than the dot itself. So our approach here was to use Braille or air. We're not the first people to try this. But as you can see here, if you just start out with supplying air to every single dot, you end up with something like this. And in the bottom picture here, you can really see what's happening. So you're going to end up with a separate pipe for every dot, basically. And that's not going to help when you're trying to make a compact, lightweight display. Now, even this display was partly interactive. You could see here where I'm able to move. This is Snake. I was able to move the little dot around the screen, but I had to use keys on my keyboard with my other hand and just track what was going on with one hand. But it is kind of interactive. So we were already looking at interactivity, though we didn't have a touchscreen integrated at this point. So then the next question was, how are we going to solve the so-called piping problem? Well, the way we did it, you can see here, this is actually expanded out. If you look at this thing, you have to look at it under a microscope because it's so these elements are so small. So what we did is we still have the bubbles that drive the dots, but we drive the bubbles with air logic. And that allows us to avoid having any moving parts in the display once we leave the edges. So we have a row and a column of valves, and then we address each dot within the display by actuating a particular row and column or a particular valve in each row and column so that they kind of basically through a sequence of valves, they address each dot on the display individually. Now, so here's the Proteus again, or this is a different prototype, the previous one actually. And here's me reading again. And you can see on this device now that I'm able to use that butterfly technique that we saw earlier, right? Because there's multiple lines. So you can see I'm able to track back from the end of one line to the beginning of the next. And this is a much more fluid reading experience. And then when I get to the end of the screen, I just hit the down button and it gives me the next 4 lines of text. And again, I'm using the device again, and this is the menu again. And you can see here that I can double tap on menu items to actuate them. And then I can just kind of, again, have this fluid interaction where I'm just going in and out of menus, moving forward and back on the display. So there's what we call co-located touch input and touch output here, which is what's making this interaction very fluid. So one of the things that we started to think about was, could we go beyond Braille and do things that are much more interesting, that basically take advantage of the fact that we now have spatial extent. We can do spatial tasks. And this is the next video I'm going to show you is an older device. It wasn't made by us, but we did this crossword puzzle where basically we substituted each letter on the display with a dot because this device didn't have the same resolution. And when you tapped on the dot, it would speak the letter. And this allowed us to explore this concept of filling a crossword puzzle.
To solve the crossword puzzle, one starts by finding the word they wish to solve on the matrix and pointing at the pin. They then query for the clue by simultaneously pressing the right arrow key for the across clues or the down arrow key for down clue. In response, the system announces clues and other textual information over speech.
Poet exiled from Florence.
And the blinking movement of the pin at the location of the word connects the announced information to a physical location on the screen, as you can see in this clip.
Was everybody able to hear that?
Yes.
Okay, so what's nice here is that Braille does take up a little bit of space. So if you want a really high density representation like this, you can actually offload some of that work to speech. So you can use cross-modal feedback in this really interesting way. So we've got co-located tactile information, but the actual words and letters are spoken to maximize the amount of information we could squish onto the tactile surface here. So now let's move on to this next part of our design process, which was to develop new techniques for interacting with Braille. And this comes from our 4th key design decision. So here we're looking at what we call the Braille user interface, or the BUI, and our goal here is to create a consistent interaction across multiple applications, whether they're on the device itself or whether they're displayed on the device when it's connected to a computer running a standard screen reader or something. So we wanted something that's as universal or at least as easy to understand as the graphical user interface. And in the GUI, you have a visual language where you have distinctive tactile or distinctive icons for different functions, and we wanted to do something similar for the tactile domain. So that's kind of one of the things we're working on at the moment. And it has benefits because you can standardize the feel of the interface across multiple application domains. Because the same symbols can equal the same functions across multiple applications. So you can see here, you have buttons, selectors, and some checkboxes and things. So we have these different prototype interactions. We also have developed this piece of software, now getting into the work that's done with NewHaptics. So this is a piece of software where we're trying to standardize not just the look and feel of buttons, but how they work in different contexts. And this is what we call Screen Bridge. So Screen Bridge can work with Word or different applications on a Windows machine right now. We'll probably extend it to the Mac shortly. But we want to be able to have these interactions to be consistent across multiple domains of work. So then, this allows us to do kind of an adaptive user interface expansion that has a more responsive Braille paradigm that basically we can fit applications into this interactive way of working. But beyond Braille, what else might be out there? Well, what about dynamic interfaces? And they certainly can exist. Here's a lovely example. So the advantage here is that when you've got co-located touch input and touch output, you can actually design real-time manipulation of objects. And you can make these temporal experiences which can extend what's possible given what we currently have available in terms of normal tactile experiences for reading and interacting with electronic or digital content. So here's an example.
All right, so now it's going to start. As you see, you've got your game board and the pieces are already moving. I can rotate the piece, but I don't want to rotate it that way. Then it's going to land, and then the next piece will start, and it'll show you the next piece up here that's coming. It's like a little L, and then what piece is following is this one. So now I might want to use both hands to start looking. And again, this is something kids will learn to line up the pieces. Ah, I missed.
So you can see what's happening here is that you've got these tactile shapes that are moving, and it's the Tetris game. So he's trying to predict where you can put them by the time they get to the bottom of the screen. So that's a really nice example of what you can do with an interactive tactile shape display, and the fact that somebody can actually, that the surface is responding to what somebody's doing as they're working with it. Another really interesting thing is that you could eventually have something like a tactile movie, provided that you take into consideration the fact that that tactile information has to be much more stripped down if it's going to make sense, especially once it's moving. But here's a really nice example from a couple of years ago.
On August 21st, 2017, the moon passed directly in front of the sun. And for the first time ever, people who are blind saw the eclipse in real time, touching the sun directly, feeling it slowly disappear.
It's working, Larry.
It is.
It did, yes. Oh, wow.
It works.
Kids and adults alike shared the experience through APH's prototype tactile display technology, graffiti.
Whoa. That's so cool.
Its 2,400 movable pins formed the image of the crescent sun, refreshing with photos from a camera pointed directly overhead.
Oh my gosh.
I know it. That's what I said.
For many, seeing the shape of the sun in real time was an out-of-this-world experience.
Ah, look at that.
Some were over the moon.
Okay, that's enough of that. Corny jokes. But what works here is the fact that the time is constant and the image is fairly simple. So I think certainly for an application like this, that makes a lot of sense. Now, it's probably unlikely that you'd be able to render a movie in real time on a tactile surface and understand what's going on. But for interactive games and certain simulations, for instance, for engineering purposes and things like that, I think there's a lot of mileage in this kind of display. So some takeaways then. So these techniques and technologies for representing information in tactile form are evolving very quickly. And methods for presenting information in one or more modalities are also moving very fast as well. These technologies now support interactive image exploration, and they also support viewing of dynamic content, as you've seen. And these tools are becoming more important for blind people because with AI, blind people are now able to access more imagery and even generate their own images, which they then want to be able to check. So they're reaching into the world of image creation and image understanding in a way that we've never done before. So tools like this are going to be really helpful to support that kind of learning and understanding. And so, after all these years of work, the Codex finally moves out of the lab. Here you can see one being assembled. And then I'm actually teaching with it. And what's really cool here is that when I'm reading my slides, if there's anything like media on my slides, I can just double tap it right there and it plays. Unlike what I'm having to do here, which is to keep track of which slides have active elements on them. And it finally also made it to CSUN, which is and you'll probably recognize this person. This is the CES of accessible technologies. This happens every year, and we've been bringing this device for the last couple of years. And in each case, Stevie has stopped by to check it out because he likes the fact that we're from Michigan, so he comes to see us. And then I want to acknowledge, obviously, our funding sources: the University of Michigan, National Science Foundation, National Institutes of Health, but also the team at NewHaptics, Alex Russomano, who was the original PhD student on the project, Brent Gillespie, who was a co-supervisor with me, and then Greg, Derek, who else is here? Dave, Stephen. There's a whole bunch of people here behind the scenes who have been doing all the work to bring this device to market since we started the company in 2019.